Welcome to another lesson of sectoral structure theory. Today we will talk about partial sums transformation. Transformations are perhaps one of the most important aspects of sectoral structures theory. They are really a study of the dynamics or the changes that happen to sectoral structures. We haven't talked so much about them yet because we don't have enough background yet. But today we'll be able to talk about the first transformation. In order to do so, we need to define a few things. We know that a sectoral structure of order lambda is made of lambda parts, and the weight of each part is the partial weight of that part. So partial in this case comes from the word part, and we're not trying to imply a division, but really just that this part has a certain weight. We call it the partial weight. We use W for weight, and for the weight of a given part I, we will say Wi. Now, every sectoral structure of degree 2 or greater has these outer parts. So these are the two parts that are at the ends of the sectoral structure. So they are the ones where the L prime and S prime ends are. And we will say that the sum of these two parts, the sum of the weight of these two parts, will be called the outer weight of the sectoral structure. So in this case, the outer weight of this sectoral structure is 1 plus 3, 4. And then the sum of all the interior parts of the sectoral structure will be called its inner weight or its interior weight. And we will put, in this case, the I before the W to not to confuse it with WI. So this is inner weight or interior weight, and this is outer weight. Of course, the sum of all of these, the inner and the outer weights, gives us the total weight, which is also called the degree of the sectoral structure. So in this case, the inner weight is 3, the outer weight is 4, the sum is 7, and we can see that indeed 7 is the degree of this sectoral structure. Let's now define a few more concepts. So we know that the outer weight, for example, can be written as n minus the inner weight. The outer weight can also be expressed as W1, so the weight of the first part, plus W lambda, the weight of the last part. And then the inner weight, it can be written as the summation of all the weights Wi from I equals 2 to I equals lambda minus 1. So again, to avoid confusion, Wi just means the weight of part I, and IW is the inner weight. So in retrospect, now I see how this can be confusing, but I think we can address it. Now we're going to define the partial sum transformation. This will be, we're going to use sigma bar to indicate this transformation. And it is from ST subscript N to ST subscript N. And notice here we're writing using the capital N. The capital N is basically, we mean natural numbers in this case. So we're saying this is the set of all possible sectoral structures of any degree. The reason we say that instead of using the small n, like we will see with other transformations, is because the degree changes after applying this transformation. So we're going to be in the realm of all sectoral structures, or the group of all sectoral structures. So we will say that sigma bar of AN is equal to BM. So here's, we're applying the transformation to AN, and we're getting a BM. Notice we used N, and then here we used M because this is likely to change. And we're going to define this transformation as follows. We're going to use the partial weight format instead of the standard format. So this is the standard form for AN, which is 3, 2, 1 squared 7, for example. When we write it in as a partial weight format, we're going to say WI, and we'll put a line here from I equals 1 to I equals lambda, and we close the whole bracket, and then we put N here to indicate the degree of the sectoral structure. So we're going to use this a lot when we talk about transformations because it makes it easier to express mathematically. So in this case, sigma bar of AN will be equal to WI plus WI plus 1 from I equals 1 to I equals lambda minus 1. And then we're going to change this to M. Let's explain what this is saying. We call any two parts that are next to each other adjacent parts. Keep in mind these two sectors here are alternating sectors, so not to confuse them with adjacent parts. Here we're talking about the whole parts. And then we call any sectors within a given part, the collection of sectors within a given part, we call them neighbors. So going back, how do we apply this transformation? So we have here, let's expand this to 3, 2, 1, 1, 7. If we apply the sigma bar, which is the partial sum transformation, we add these two. So 3 plus 2, we add each two adjacent parts. 3 plus 2 gives us 5. 2 plus 1 gives us 3. 1 plus 1 gives us 1. And the degree changes to 5 plus 3 is 8 plus 1 is 9. So when we applied this transformation, the order went from 4 to 3, but the degree increased from 7 to 9. So this is what we mean by a partial sum transformation. So what do we know about M in this case? We saw we went from 7 to 9. Can we generalize this? And the answer is yes. We'll say M, the easiest way to express it is equal to. So think about it, we're adding each of this, so we're adding each part once to the left and once to the right. So really N is going to double, so it will be 2N. However, there is the exception of the two parts that form the two terminal parts or the two outer parts of the structure. These will only be added once. So what do we say? We can say that M is equal to 2N minus the outer weight. So for example, here 7 times 2 is 14 minus the outer weight, which is 4. So 14 minus 4 is 10. So that means there was an error. Let's see. 5, 2 plus 1 is 3. And then 1 plus 1 is 2. This adds up to 10. Sorry. So that was a mistake. So really it's 3, 2, 1, 1. What we need to do is 2 plus 3 is 5, 2 plus 1 is 3, and 1 plus 1 is 2. So it adds up to 10 indeed. So really this helped us catch that error that I made. Another way to express this is by substituting into this equation n equals inner weight plus outer weight. And what we end up with is m equals to n plus the inner weight. So if we want to find the weight after the transformation, we can either say n plus inner weight or 2n minus outer weight. This is usually easier because you never know how big the inner part is. Let's go back to this example which we just looked at. So 3, 2, 1 squared 7, we already applied the sigma transform or the sigma bar transformation, and it gave us 532 subscript 10. Now, if we want to apply it twice, we will say sigma bar squared of an, and then we're going to say 5 plus 3 gives 8, 3 plus 2 gives 5. Notice this became 13, the n became 13. And then if we want to apply it again, we will say sigma bar cubed of an equals to 8 plus 5 is 13 subscript 13. Now, if we apply it more times, it's just going to keep giving us 13. So once we reach a theta structure, the theta structure, which is basically a closed circle divided into equal sectors, then applying the partial sum transformation just gives us the same theta over and over. We've already looked at the order, how the transformation affects the order. So we know the order of the order post-transformation. So lambda of sigma bar an is equal to the order prior to the transformation, so order of an minus 1. So each time you apply the transformation, you lose 1 unit of order. However, this only applies when lambda is more than 1. Once you reach a theta structure, you don't go to 0, you stay at 1. Additionally, we can say, if we apply the transformation multiple times, we will say that lambda of sigma bar to the power of x of an is equal to lambda of an minus x. So if I raise or if I apply the transformation 5 times, the end result will be 5 units of order less. However, x must be less than lambda. So if a structure is made of 3 parts, you can't use this formula to figure out what the order will be after 10 transformations, because once you hit a theta structure, nothing changes after that. So that's a key concept. So another way to say this is sigma bar of theta subscript n equals to theta subscript n. Now let's look at a little bit more of what we will call the sectoral series. If I have an and I apply sigma bar of an and then sigma bar squared of an, each of these will generate a different sectoral structure. I can keep doing this until we reach the final theta structure. So I can keep applying this lambda minus 1 times until I reach a theta structure. So this theta structure for a given sequence of that form, or what we're calling a sectoral series, will be called its convergence structure. So the convergence structure is the theta structure at the end of many transformations, many partial sum transformations, and we will say theta subscript c for convergence. We saw in this example that the theta c of this structure was 13, 13, or theta 13. We will also use the notation C bar of AN to indicate the convergence structure of AN. So C bar of AN is equal to sigma bar to the power of lambda minus 1. So that's how many times we apply it, of AN. And this will give us theta C. So going back, C bar of theta n is equal to theta n, because you can keep applying this to a theta structure many times and it will stay the same. Now let's look at the xi structures. If you remember, the xi structures are the ones of the form 1 to the power of n subscript n. So this will be, for example, 111 subscript 3, or 1 to the power of 8 subscript 8. So for a xi structure, let's look at 1 cubed subscript 3. So this will be 1, 1, 1. If we apply the sigma bar to this, we will get 2, 2 subscript 4. So notice we went from 3 to 4, and this became 2, 2. If we apply sigma bar again, 2 plus 2 is 4 subscript 4, and that is our convergence structure. So the convergence structure for xi 3, or 1 cubed 3, is equal to theta 4. So the case of the xi structures is unique because we can figure out, we can easily predict the theta or the convergence structure for a xi structure, no matter how large it is, without having to go through the entire algorithm. We will say that C bar of xi n is equal to theta, because that's the convergence structure. But what degree is it? It will be of degree 2 to the power of n minus 1. So for example, if we have the structure, let's say 1 to the 4th subscript 4, that is a xi 4 structure. What is its convergence structure? We will say it will be theta 2 to the 4 minus 1. 4 minus 1 is 3. 2 to the 3 is 8. So it will be a theta 8. And you can double check. So we will say that C bar of xi 3 is equal to theta 4. So that is a very interesting way, or a very interesting case of the convergent structures. Let's look at another example. So we will take the sectoral structure xn is equal to 421 subscript 7. We will say, we'll use a big sigma. In this case, we'll say T sigma of xn. What is that? So if you remember, whenever we put the T, it indicates set, basically, in this case. And sigma, just to tell us that we're talking about the partial sums. So T sigma of this sectoral structure xn is basically the set of sectoral structures that are generated along the way of the partial sum transformations between xn and its convergence theta structure. So let's look at it. So we will say T sigma of xn is equal to the structure itself, so 421 subscript 7. We apply the sigma bar transformation to it, we get 6, 3 subscript 9. So that's the second structure in this set. And we do another partial sum transformation. We get 9 subscript 9, which is the convergence structure. So together we will say that these three structures form the T sigma set for the sectoral structure Xn. Or we can just call it the sectoral series set for Xn. And of course, C bar of Xn, or the convergence structure in this case, is theta 9. Now I want to show you how this is a little bit trickier than it first seems. Let's look at the convergence structure 8 subscript 8, or theta 8. Now we will see that the convergence structures are not just the convergence of a single sequence, but they are the convergence of several sequences. So I'll write theta 8. We want to find the structures that give us theta 8 when we apply a sigma bar transformation to them. So we know that they must be one order higher, and they must add up, their parts must add up to 8. So this gives us 4 possibilities. We have, let's start from here, 7, 1 subscript 8. We have 6, 2 subscript 8, 5, 3 subscript 8, and 4 squared subscript 8. The 7, 1 subscript 8, because we have a 1, whenever you have a 1 in a sectoral structure, if you remember, that of course makes it an irreducible sectoral structure. But in this context, there is no way you can add 2 parts and get 1, because we're only looking at natural numbers. So 7, 1 subscript 8, you cannot find any sectoral structure that you can apply a sigma transformation to and you'll get this. So this is really like the dead end of this tree. So 7, 1 ends up in in theta 8, but there's nothing before it. Let's look at 6, 2. 6, 2, if we want to apply a theta transformation and get 6, 2, then we need a structure with 3 parts. So in this case, we need 2 numbers that add up to 6, and then 2 numbers that add up to 2. So for 2, there's really only 1 plus 1, so this really makes it easier. So we have 1 here, 1 here, then this must be a 5. And that's the only possibility. So 5, 1 squared subscript 6. And because there are 1s, this tree also ends here, or really begins here. Then we can look at 5, 3 subscript 8. We find that there's also only one sectoral structure that can be transformed into it, and that is 3, 2, 1 subscript 6. And because there's a 1, this is the beginning of this particular tree. Now 4 squared subscript 8, there's 2 ways to get this. One is 3, 1, 3. So 3 plus 1 is 4, 1 plus 3 is 4. So this is one possibility, and this one ends here. The other possibility is 2, 2, 2. 2 plus 2 is 4, and 2 plus 2 is 4, so 2 cubed subscript 6. And this one is actually born out of a zeta structure, a xi structure, which is 1 to the 4th subscript 4. So this is really the longest branch of the tree, which we will be the most interested in if we're trying to find the longest path. But this is also special because it gives us, because it is the longest part, it gives us the part or the sectoral structure of the largest possible order, such that we can apply a number of partial sum transformations to it and end up with theta 8. So all of these sectoral series converge onto theta 8. And another way to think of it is we can call this the convergence field of theta 8. So these are all the possible sectoral structures that can converge on theta 8. This takes us to our final point we want to mention before we stop, which is the inverse function of the partial sum transformation. We will indicate it as sigma bar to the power of -1. But another way to call this will be the partial difference transformation. Uh, or maybe we'll just call it the inverse of the partial sum transformation. So let's look at an example. We have the sectoral structure 423 subscript 9. We want to find the inverse partial sum for this sectoral structure. So we want to find a sectoral structure such that if we apply the partial sum transformation to it, we end up with 423 subscript 9. So this structure has an order of 3. In order to have a structure or sectoral structure that can be uh, we can apply the partial sum to and get this structure, it must have an order of 1 greater. So it must have an order of 3 plus 1 equals 4. Remember, order is the number of parts. We can even predict what the degree of this sectoral structure will be by rearranging this equation here. We know that m is equal to n plus inner weight. We can say then that n will be equal to m minus the inner weight. M in this case is 9. The inner weight is simply this interior part, which is 2. 9 minus 2 is 7. So the sectoral structure, we know two things about it. It has an order of 4 and it has a degree of 7. So we can write this as an equation. We will say that sigma bar of an equals 423 subscript 9. Therefore, an is equal to the sigma bar inverse of 423 subscript 9. And I wanted to introduce this equation because later on we're going to be using more of these. So we know this result should have order 4, so it has 4 parts that add up to the degree of 7. What else do we know? We know that the first two parts must add up to 4. So we have two possibilities, either 3 plus 1 or 2 plus 2. Now we know that the second part plus the third part must add up to 2. So this really gives it away because there's only one way to do this, and that is 1, 1. So 1, 1. We go back now to this first part. We know this must be a 3 because it has to be a sum of 4. And the last part here was a 3, so we know that 3 and 4, or part 3 and part 4 must add up to 3. We know this is a 1. 3 minus 1 is 2. So therefore, an is equal to 3 1 squared 2. Let's double check the degree. 2 plus 2 is 4 plus 3 is 7. Indeed, it is correct. Let's apply the sigma bar transformation to an. So 3 plus 1 is 4. 1 plus 1 is 2. 1 plus 2 is 3. Subscript 9. So it is correct. And this will be our first partial sum equation. But basically, this is the simplest form, but it can get more complicated if, for example, we do something like this. If we say sigma squared of an is equal to something else, or if we start trying to do more equations, which we will do in the next lesson. Thank you.